So I will talk about a technology and business opportunity. My name is Jung Han. I'm a professor of electrical engineering at Yale. And we have an idea of a blue laser diode company, and we call it LaPor. So it's a laser company with a particular technology we call it porous technology. We focus on blue laser diodes, and this is already there's an existing market in projection, in automobile lighting. So it's projected to grow to 1-2 billion in the next few years. And I will just quickly talk about the opportunities or the problems. Currently, there are two major manufacturers or leaders in the blue laser diode world. One is in Japan, one is in Germany. And in this slide summarizes the current, pretty much the state-of-the-art blue laser diode technology. Here, if you look at the current density, the amount of current you put into diode laser, and versus the optical output, we call it efficiency. So when you push current into laser diode, normally initially there's a zero efficiency that's below threshold. And once you reach what we call lacing threshold, then it starts to go up. But all the current, even the best laser diode reaches only close to 40%. This is a research lab result. In fact, the commercial blue laser diode typically stay at about 20–25%. And so you can see there is a tremendous room to grow. The current blue laser diode require a lot of thermal management because it generates a lot of heat due to the inefficiency. So what we are proposing is with the use of our technology to move the technology to the blue curve. First, we reduce the lacing threshold and improve the overall efficiency to about and over 60% based on our simulation. I'll just say a little bit about the technology. And the left, this chart shows a typical construction of a laser diode. Basically, you have a rectangular bar, and the front and the rear ends or facets, those are mirrors. So we have a resonator with the two reflectors. So light travel back and forth this way, and interacting with an active lacing medium to get amplified. Okay, so there are many issues that could account for the reduction of efficiency. But one important one, that the big issue for the particular material system we are dealing with, gallium nitride, is it's relatively difficult to confine the traveling light back and forth. So there's not enough index of we call the optical confinement. So on the right, I just show that the cross-section looking into this facet, this light tends to diffuse and it does not interact with the active medium in the most effective way. And our solution, which we demonstrated, is to tighten this optical confinement using a special cladding layer to squeeze the optical field, making the optical field very concentrated near the lacing medium. In that way, we can enhance the interaction of optical field with the lacing medium, enhance the optical field by 3 times, and then improve the overall efficiency by 2 times. So the way to do it is to incorporate some tiny air bubbles or voids into gallium nitride. And we have a a patented rather special technology using electrochemical process to convert and make gallium nitride porous. Once gallium nitride becomes porous, it will effectively guide the optical waves, and this process is scalable, very controllable, and very inexpensive. And so we have some initial result. We demonstrated the lasing. I'll just focus on here, where we use a different air bubble sizes to change or to improve or enhance what we call confinement factor gamma. So this factor measures how tightly, how strongly we can confine the optical field near, around the active region. As we go from 4% to 9%, you can see this is the input power and this is the laser output. So as the number increases, then the lasing threshold dropped by more than a factor of 2. This is exactly what we want, and this will improve also the overall efficiency. So this we consider is a proof of concept demonstration. So this is our business model. Currently, we're here. We have the proof of concept demonstration, and we are seeking an angel round funding. And by doing so, we could generate a prototype of the laser diode in roughly 2 years. And beyond that, for the next round, we consider either we could license the technology to existing big laser diode companies such as Osram or Nichia, or we continue to push the technology up and manufacture. This is option B. So thank you.